this is our first video on Taylor polynomials. I've divided this into two, so this will be part one. You have all the notes for this, and so you'll just need to watch this part, and then next night you'll watch the second part. So we've been working on series and whether they converge or not. So here's part of the reason that we needed to learn that, and that has to do with something called Taylor polynomials that can be used to approximate other functions. And then after we talk about Taylor polynomials, then we'll talk about series. And so then that's where all that stuff will come into play about whether things converge or diverge and all of that. So we're going to talk about what a Taylor polynomial is and how it helps us here. So first example, we're going to find the equation of a tangent line for sine x at the point x equals 0, and we're going to approximate sine of 0.2 with that. I'm going to get the calculator going because we're going to need that in a minute. And then we want to know if it's an over or under approximation for sine of 0.2. So we remember, and this is a good review for us, if we want to write an equation of a tangent line, well, if we want to write an equation of any line, we need the slope, and then we need a point. And so to write the equation of a tangent line, we're going to find the derivative. And so we will find the derivative first. So let this get started. And then I'll get it out of the way, and then we'll get to our derivative. Or you can do that on your paper. Find the derivative of sine x. So the derivative of sine x, if f of x is sine x, then the derivative is cosine x. And then we want to find the derivative at x equals 0. So f prime of 0 would be cosine of 0, which would be 1. So we know that our slope of our tangent line is 1. And then our original point is x equals 0. If you plug 0 in here, you're going to get sine of 0, which is 0. So our point is 0, 0. So that means we would have, if we go the long way, y minus the y value, which is 0, equals the slope, which is 1, times x minus the x value, which is 0. So we end up with an equation y equals x. So what we are supposed to do is use this to approximate the value of sine of 0.2. So sine of 0.2 is approximately equal to plugging in 0.2. We're using this function to approximate it. Well, if we plug in 0.2, we're just going to get 0.2. And then we want to know if it's an under or over approximation. So here's what we're going to do to look at that. We're going to think about what the graphs look like to decide whether this is an over approximation or under the real value a little bit. So if we were to draw the sine graph, and we could just draw a little bit of it, and then we were to draw the line y equals x, we're going to get a line, well, my sine graph is really bad here. Let me draw it a little bit better. And we're going to get that they are pretty close to each other. When you're close to 0. So when we're kind of in this area, the tangent line is pretty close to the values of sine. As we get further away, not so close, like obviously as you get over here, the values are not very close, but really close to 0. This is probably a pretty good approximation. Now, because the sine graph is concave down and increasing, then your tangent line is above it, which means this should be an over approximation. Okay, because looking at that line, you can see that this is going to give me an over estimate of any values in that area where 0.2 would be, which would be over here somewhere. We're going to get an over estimate. So let's actually see what sine of 0.2 is to see how close we were. So if you take your calculator and do sine of 0.2, you're going to get 0.19867. So 0.2 isn't a bad estimate at all. It's actually pretty close. Well, that's the idea of a Taylor polynomial. And so we would call this one a first degree Taylor polynomial because we only use the first derivative. And the idea is that we're going to make the function, we're centering it at 0 here in this case. So we want the function and its derivative to have the same values at the first derivative, means it's a first degree polynomial. If we want to include the second degree or the second derivative, then that means we want the function and the first derivative and second derivative to all have the same values when x is 0. Then we can continue adding the third derivative, fourth derivative, fifth derivative, and every time we want the function value and the values of each of those derivatives to be the same. So the more we have, then the more that we have them the same. So let's look at what that kind of looks like. So on your calculator, we're going to graph this a little different because we have an Inspire calculator, so we can do ours a little different. So you're going to add a graph, and you're going to graph first sine x. So we do want to do that part of what it says. So we're going to make the graph y equals sine x and hit enter. And then it tells us to use the viewing window -9 to 9 and -4 to 4. Now a quick way to do that when you know all the things you want to change is go to menu, window zoom, and use number 1, window settings. It tells us to go -9 to 9 for x, and then over here on y, -4 to 4. Alternately, you could have gone through and clicked, double clicked and everything and gotten that the same, but this is what it asks us to use. Then what we're going to do is we're going to do it a little different. We're going to graph each of these parts one at a time. So in y2 only, I'm going to graph just y equals x. Then in y3, I will graph this. And then in y4, I will graph this, and so on. And we're going to look and see how close we get. So let's hit tab, and let's go ahead and graph just y equals x. So this is the situation we just had. This is exactly what we just did a second ago. So there you see the sine graph, and then you see the y equals x graph. And again, you can see how they're pretty close when you're near 0, but if you get far away from 0, they're not even close at all. Well, so then what we're going to do is we're going to add to that, and you'll see why I'm using the things I'm using later, but right now just follow along. So I would have your calculator out and be doing this too. So you're going to graph now x cubed over 3 factorial in addition to the x. So x minus x cubed. Well, I can get it to type what I'm pushing. Goodness, that'll work. All right, over 3 factorial. Remember your factorial button's there next to the G. Well, that's funny, it didn't show up there, but it's there, I think. All right, and hit enter. No, it did something weird. I don't think that's right. All right, so then we add another one. So we want the same graph that we had before. So we want to do x minus x cubed over 3 factorial, which is 6. So I'm actually just going to put 6 here. That's quicker. And then plus, and then we want to do x to the 5th. My stuff isn't working. X to the 5th over 5 factorial. Let me get it, the factorial from here, make sure I'm getting the right thing here. Yeah, it just looks funny on my screen. So, okay, so then we have this. Now notice that the more and more we go, and you can go ahead and do it one more time, but you should notice that you can see that the further we go, you can see that the blue one at least follows it a little bit longer, and then it kind of comes off here and doesn't really meet it, and then the purple one goes further around that it stays the same until it starts to go off. And if we continue like that and keep adding and do another one, then we're going to get even closer further away. So the farther and farther from zero, the closer we'll get. So this is an example. This graph right here is an example of a Taylor polynomial, and it's going to show us some things. Now, I'm not going to do this on the video, but you're welcome to do this by plugging in to each of these functions, which we've now saved because I typed them in. So I can just open a calculator page and I can evaluate each one of them at 0 or 0.2 to find out how close they were to the actual value. So like if I do F1, I can just type F1 and then put my parentheses and type 0.2, and it's going to give me 0.198669 and so on, because that's my first function evaluated when I put 0.2 in. And then I could do F2, which would be x minus x cubed over 3 factorial. It would give me a value and so on. And so I just keep doing that and I can check, and you'll see that they are all super, super close together. Okay, they all give a very good approximation. So that's what we're going to be working on, is getting toward that. So let's go ahead and talk about what a Taylor polynomial, or what we're talking about here. So an nth degree Taylor polynomial means that we have basically, this is the polynomial, and when you look at it, it looks really scary as you look at this formula and you think, oh my gosh. But if you look at it carefully, you'll realize that whatever the derivative I'm taking, so second derivative, I'm dividing by 2 factorial and the power is a 2. So if I'm on the nth derivative, it's n factorial and it's n for the power. So it's actually really pretty simple, very easy to remember. We say this one is centered at x equals c, and what that means is that you are guaranteeing that, say we only went this far and we just had the second degree, we're saying that the original function, the first derivative, the second derivative, all have the same value at c. So that means close to c, this is a really good approximation. So maybe it's at x equals 1. Well, then you can approximate the value of the function close to 1, and this would be a very good approximation. The further you get from 1, it's not as close. Okay, so that's what we're talking about. Now, first degree one is basically nothing but the tangent line. So if we do a first degree one right here, that's nothing but a tangent line, and that's what it's asking for. All right, so we go to another term which is called a Maclaurin polynomial, and all this is a Taylor polynomial, but the center is 0. So it looks very similar, you just don't have x minus c here, and you're evaluating everything at 0. And you'll see when we use these, it's much easier to remember. But these are always, this is really important, always approximations. These are polynomials, they end somewhere, they're always an approximation. Okay, so let's actually go through one so you can see the process here. So we want to find a Maclaurin polynomial of degree n equals 5 for f of x equals sine x. Now, another thing I want you to do, if you have not done this on your calculator, I want you to go to Doc, Settings, and I want you to do your document settings, and I want to change your display digits to float. So you can pause the video and get that done, and you want to do that because these are going to be so close, we're going to need a whole bunch of digits before we can tell the difference. So get your calculator changed to float so that in a minute when we plug some numbers in, you'll be able to see that. All right, so we're going to use this and find the 5th degree polynomial. So I like to make it very organized, and you'll be able to easily follow what you're doing. So to do the 5th degree polynomial means I'll have to get to the 5th derivative. So f of x is sine x. F prime of x, derivative of sine, cosine. F double prime, derivative of cosine, is minus sine. F triple prime of x, the derivative of sine is cosine, so we'll have to keep the negative. And then remember, when you get past triple, you start using Roman numerals. So that's f4 of x, or you can use the number 4. I'll do that on the fifth one. So I take the derivative again. The derivative of cosine is minus sine. I already have the negative there. And then fifth degree. So you can use a regular 5 also. You'll see it both ways. One more time, derivative is cosine. So that's going to be all the things I need in my formula, except I need them all evaluated at 0. Maclaurin Polynomial tells me x equals 0. So I'm just going to write right next to it f of 0, which would be sine of 0, which would be 0. F prime of 0, which would be cosine of 0, which is 1. F double prime of 0, well, it has sine in it, so it's going to be 0. F triple prime of 0 is going to be negative 1. Fourth degree here at 0 will be 0 again because you have sine, and then your fifth degree is going to be 1. And these numbers right here, and then the factorial that goes with them, are all of your coefficients. I guess it's really these numbers right here. So these are all your coefficients that are going to go in front of this polynomial. So to do the fifth polynomial, you put a little 5 there, which says that you're doing this up to the fifth derivative, and you're going to put all these terms together. So if you can look right above this example is the format for this polynomial. So just look up there and look at this example. The first thing we write is f of 0. Well, f of 0 is over there on the left. It's 0. Then we write plus, and we do f prime of 0, which is 1, times x to the first, plus. And we do f double prime at 0. Well, that's 0, and then we're supposed to divide by 2 factorial x squared. Then we do f triple prime at 0, which is negative 1. We divide it by 3 factorial x cubed, plus f4, which is 0, over 4 factorial x to the 4th, plus 1 over 5 factorial x to the 5th. And so now you can see how it actually goes really fast. Once you have these numbers, that's all you really have to fill in. The rest of it's just a format. Now let's write that a little bit nicer because we don't need all those terms that say 0. So this is our polynomial. So we have a 0, and then we have a 1 times x, that's x. Then we have a 0. Then we have a minus x cubed over 3 factorial. Then we have a 0, and then we have a plus an x to the 5th over 5 factorial. So this is our Maclaurin polynomial, 5th degree, because I went to the 5th derivative. All right, then it says, well, let's use this to approximate what is sine of 0.1. So if we do this polynomial evaluated at 0.1, we're going to get the approximate answer for sine of 0.1. And when we do this, and I should have put that in the other order, but that's okay. If I do this in the calculator, so take your calculator and do plug in 0.1 here, 0.1 here, 0.1 there. So actually do that in your calculator, and you will get 0.998334167. And that's where I was telling you change it to float. Otherwise you won't be able to see that. So do it in your calculator and make sure you do get that answer. All right, then it says compare your, then it says determine an interval where sine of 0.1 could actually live. Well, here's what they're talking about. Remember, if we have an alternating series, that we can find the approximate, we can find that the error is no more than the next term. Well, so in here, non-zero term. So the next term here, if I were to keep going, the next one would be minus x to the 7th over 7 factorial. You can certainly see the pattern now. If I kept going, it would be plus x to the 9th over 9 factorial and so on. So what we're saying is, since this is an alternating series, the most I can be off is this, x to the 7th over 7 factorial. It's plus or minus that. Well, if you do that in the calculator, you get 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 198. So our approximation is plus or minus that number. So that's the interval that includes the true value. So if I want to actually write the interval that our actual answer lies in, I need to take this number and subtract this and that number and add that, and that's my interval. And if you do that in your calculator, this is what you're going to get on each side. So that's taking that error and adding and subtracting it to that estimation that we got. So we know that somewhere in there is the actual value. Well, if you do sine of 0.1 on your calculator, you're going to find that you are in that interval. So if we actually do sine of 0.1, so let's do that and move it over here to the side where we can see it. So let's do sine 0.1 and hit enter, and we can see that our answer is definitely in that interval. If you look carefully, we do fit in there. It doesn't differ until right here, but this is let's see, 416. This is 67. The calculator is giving me 416,647. Let's see, 0.0998334,166. I wonder if I needed one more. Oh no, this was 6. I wrote this wrong. This was 146647. And this one was 87 on the end, and our actual answer ends up actually right in here. So this was a very, very good approximation. Plus, this is, again, the most we are off. The most we can be wrong is that many places. So it's a very good approximation. So that's why this is can be very valuable. All right, so let's do another example. The more you do these, and will make a lot more sense. So just go ahead and practice with it. And when you do the homework, it'll start to make more sense. Really just learn the process, and then it'll make a lot of sense later. Okay, so here we want to find the Taylor polynomial again, degree 6. So that means we need to find f, f prime, f double prime, etc. down to the 6th derivative. So our first function is ln of x. So we want to take the derivative of ln of x, and we know we get 1 over x. We take the second derivative. Well, that means the derivative of 1 over x. Well, you should know this one. We've done it so many times. It's negative 1 over x squared. But just remember, this is just x to the negative 1. So put the power in front, lower the power by 1. And you're going to keep doing that. It's not going to hurt you to practice these. Like if you need to rewrite all of these so you can actually do the derivatives, that's a good practice to do. So this will be 2 over x cubed. Your fourth derivative is going to be, you'll have a 3 times that 2, so you're going to get 6, and then negative x to the 4th, and then you do the fifth derivative, and you're going to get a 4 times the negative 6, only negative, so you'll have 24 over x to the 5th, and then to do the 6th derivative, you're going to get 5 times 24, and then it alternates, so it's negative, so it's negative 120 over x to the 6th. Always look for patterns, especially when you're doing these problems, because a lot of times it'll just come out and end up being really easy when you thought it wasn't going to be. Now we're supposed to do a Taylor polynomial, so now it's centered at 1. So that means we're plugging 1 in each time. So this is ln of 1, which is, of course, 0. Then you're going to plug in 1 to the next one, which is going to be 1 over 1, which is 1. And then you're going to plug in to the second derivative. You plug in a 1, so you're going to get negative 1. Third derivative, plug in 1 for x, and so you're going to get 2. Fourth derivative, plug in a 1 for x, you'll get negative 6. fifth derivative, plug in a 1 for x, you'll get 24. Sixth derivative, plug in a 1 for x, you'll get negative 120. Now remember, these numbers are all those coefficients, and then they get divided by whatever factorial, whatever term you're on. All right, so we're going to use all of that to write out the polynomial. So we're supposed to do the sixth polynomial. So the first thing we start off with is f of 1, and f of 1 because it's the first one, which is 0. Plus, then we take f prime at 1, which is 1, times x minus c this time, which is 1. So each of these will just have an x minus 1 in them instead of just an x. Then we're at the second derivative. Well, the second derivative is negative 1, so this will be negative 1 over 2 factorial x minus 1 squared, plus next number, f triple prime, is 2, so we'll have 2 over 3 factorial x minus 1 cubed. Then it's coefficient over 4 factorial x minus 1 to the 4th, and then it's coefficient over 5 factorial x minus 1 to the 5th, and then it's the coefficient over 6 factorial x minus 1 to the 6th. So we could get rid of the 0 at the beginning, and then we can straighten this up a little bit. This is x minus 1, and then instead of plus, since it's negative, we'll write minus, and it's really just 1/2 x minus 1 squared plus. Now, if you remember, 3 factorial is nothing but 3 times 2, so this actually becomes 1 over 3 x minus 1 cubed. Then we'll have minus 4 factorial is 4 times 3 times 2 times 1. Well, that's 6. So that 6 and that 6 will cancel out. So you'll end up with minus 1 over 4 x minus 1 to the 4th. You should be able to see the pattern now. 1/5 x minus 1 to the 5th, and then minus on the end because we're alternating. And so you'll have minus 1 over 6 x minus 1 to the 6th. So definitely always be looking for patterns, because you'll find that it actually usually simplifies out a lot easier. Now, if we use that to approximate, if we were to do P6 of, we're supposed to approximate the value of ln of 1.1, we put that in the calculator, and I'll let you do that on your own, but you should try it and make sure you're getting the same answers. This is what you're going to get, and we know that this answer is approximately ln of 1.1. And you can do in your calculator ln of 1.1 to see how close we get. So this is what we will practice in class. We'll do a whole bunch of these, and so really it's just a lot of learning. Just write down all your derivatives, evaluate it at a number, fill in the formula, and we'll do all that first, and then you'll have another video which will talk a little bit more about how to use those. So that's the end of part 1.